Hello friends, I welcome you on my channel Engineering Mathematics DJ Ganit. From this lecture onwards, we are going to discuss this new topic, applications of integration. We are already familiar with the application of integration from 12th standard. We have seen in 12th standard that using definite integral, we can decide the area of the region bounded by given curve. If you recall, we have studied in 12th standard that suppose this is the graph of function y equal to fx, and suppose we are interested in the area under this graph y equal to fx between the lines x equal to a and x equal to b. Suppose the area under the graph of this function y equal to fx between x equal to a and x equal to b is this shaded region R. Then we know that area of this region R, which is bounded by this curve y equal to fx, x axis, and the lines x equal to a and b, is given by integral of this function with respect to x from x equal to a to b. This is the application of integration or application of definite integral, which we have studied in 12th standard. So we are going to discuss this also in this topic, and we will discuss another application of integration, that is we will discuss how we can find out volume of solids using definite integrals. So in this lecture we will focus in this application of integration. We will see how to find out area between given curves using definite integral. So for that we understand, suppose this is xy plane, and suppose I have two curves. Suppose this is the graph of y equal to fx, and suppose somewhere here we have graph of y equal to gx, and we consider the area between these two lines, say x equal to a and x equal to b. So here suppose we are interested in the area of this region which is bounded by y equal to fx, y equal to gx, and x equal to a and x equal to b. Area bounded by these four curves y equal to fx, y equal to gx, x equal to a and x equal to b, or we can say that area enclosed between these curves. So sometimes they can write area bounded by given curves, or they can write area enclosed between given curves. So both are same thing. So how to find out area of this region R using definite integral? So for that we can write the formula. We will integrate from x equal to a to x equal to b, and the difference of these two, upper function minus lower function. Our function at the top is fx and function at the bottom is gx. We will take difference of these two, and integral with respect to x from a to b will give us the value of area between curves. Here we have assumed that this fx is the top function, that is value of function at any point x is greater than or equal to value of function g at any point x, where x is in between a and b. So we will discuss one problem related to this. Here we have written this as a remark, that the area A of the region bounded by the curves y equal to fx, y equal to gx, and the lines x equal to a, x equal to b, where f and g are continuous and fx is greater than or equal to gx for all x in closed interval ab, is given by a equal to integral a to b fx minus gx dx. And this is another figure showing this geometrically, that suppose upper function is y equal to fx lower function is y equal to gx, and suppose we consider these two lines, area between x equal to a and x equal to b, then this is the area shaded by these lines, and region of this area is given by integral from a to b, function at the top or upper function minus function at the bottom, that is lower function. So we can remember in this way, area of the region between two curves is given by integral of upper function minus lower function with respect to x from a to b. We understand this with the help of one example. Determine the area of the region enclosed by y equal to x square and y equal to square root of x. So here we are given two curves and we know that both are parabolas. Now whenever we want to find out the area enclosed by given curves, first step we will do is we will find out the intersecting points of given curves. So see, if I want to find out intersecting points of these two, I can put y equal to x square here, or I can put y equal to square root of x here. So we can find out intersecting points by taking y equal to x square in y equal to square root of x. So we try to solve this. We are taking y equal to x square in this equation. So this is going to be, therefore, x square minus square root of x equal to 0, because x can be 0 also, so we cannot cancel out square root of x. So this is, now we can write square root of x, we can write x square as x into x, and x can be rewritten as square of square root of x. This is going to be 0. Or another thing we can do is we can square on both sides. Okay, so we can go in that way also. So here we can take square root of x common from these two terms, and here we are left with x into square root of x minus 1 equal to 0. Therefore square root of x equal to 0, or x into square root of x minus 1 equal to 0. So one possibility is x equal to 0. Another possibility is x into under root of x equal to 1, or we can say that x raised to 1 into 1 plus 1 by 2. So this we can rewrite as x raised to 3 by 2 equal to 1. Therefore x equal to 1 raised to 2 by 3, or x equal to 1. So we obtain two values for x equal to 0 and x equal to 1. So we can obtain corresponding values of y from here. When x is 0, y is 0. When x is 1, y is 1. So we can write that when x equal to 0, y is 0, and when x equal to 1, y equal to 1. Therefore 0, 0 and 1, 1 are intersecting points of given two parabolas. Are intersecting points. Now this we can simplify in this way also. Suppose you don't want to go in this way, you can take square on both sides. Suppose I square on both sides, here I can write another way of doing the same thing. I am squaring on both sides. Square of x square is x raised to 4. Square root of x is x. Therefore x raised to 4 minus x equal to 0. Therefore x times x cube minus 1 equal to 0. Therefore x equal to 0. Another possibility is x cube minus 1 equal to 0. Therefore x is 0 and x cube minus 1 can be rewritten as x minus 1 times x square plus x plus 1 equal to 0. Therefore x equal to 0, x minus 1 equal to 0, and x square plus x plus 1 equal to 0. So from this we obtain x equal to 1. And if you observe, this equation has no real root. There is no real value of x which satisfies this equation. So it has imaginary roots, therefore we will not consider this case. So there are two possible values of x equal to 0 and x equal to 1. And when x is 0, y is 0, therefore one intersecting point is 0, 0, another intersecting point is 1, 1. So first step we have to do is decide the intersecting points of given curves. Now second step is sketch the region of integration. So once we decide the intersecting points, we can sketch the region of integration. And we must sketch the region of integration. Using region of integration, we will decide that which function we have to consider as upper function and which function we have to consider as lower function. This is suppose x-axis. Here I have y-axis. First we will locate intersecting points. Suppose this distance is 0, so and this much scale is 1. So here also we consider this much scale as 1. This is going to be 0, 0. Here also this scale we have taken as 1. So our another intersecting point 1, 1 is somewhere here. This is the point 1, 1. Now our curves are y equal to x square and y equal to square root of x, and this I can rewrite by taking square on both sides. I obtain y square equal to x, and this x square equal to y is the parabola which opens in upward direction, and y square equal to x is the parabola which opens to the right. So we are already familiar with these two shapes, and we will take note that these two are intersecting at origin and 1, 1. So both are passing through these 2 points. So first we sketch y square equal to x. So for that let me sketch roughly. We require rough sketch, but we should be careful that our curve must look like a smooth curve, because we are sketching a parabola. Suppose this is y equal to square root of x, and it is passing through 0, 0 and 1, 1. Another curve is x square equal to y, or y equal to x square. So it is a parabola which opens in upward direction. Let me sketch properly. So I have to take care that it looks like a parabola. So it is passing through 0, 0 and going through 1, 1. So suppose this is y equal to x square, and this point is 1, 1, this point is 0, 0. So this is the region whose area we are interested to calculate. So we are interested in the area of this region. This region lies between x equal to 0 and x equal to 1. Here upper function is y equal to square root of x, and lower function is y equal to x square. So from the sketch of the region, we will be able to decide that which function is upper function and which function is lower function. So first we have to decide intersecting points, then we will sketch the region whose area we are interested to calculate. So here now it is clear that upper function is y equal to square root of x, lower function is y equal to x square, and x lies between 0 and 1. To find out limits of integration for x, we will concentrate on leftmost point and rightmost points of the region. Leftmost point is this one. At this point value of x is 0. Rightmost point is this one. At this point value of x is 1. Therefore limits of integration are from x equal to 0 to x equal to 1. So now we can calculate area between two curves, or area enclosed by y equal to x square and y equal to square root of x is capital A equal to integral from 0 to 1 upper function, which is x square, which is square root of x. Okay, be careful, here upper function is square root of x and lower function is y equal to x square, and that we can get the idea after the sketch of the region. Okay, otherwise you may be misunderstood that because we have x square it will be a upper function, but here x square is the function at the bottom and function at the top is square root of x. So the idea that which function we have to consider as upper function and which function we have to consider as lower function, that idea will come from the sketch of the region only. So don't decide upper and lower functions simply from the equations of given curves. Otherwise you may be misunderstood. Here you may be misunderstood in this way, that x square is bigger than square root of x, therefore x square can be upper function and square root of x is lower function. But that is not the case here. In between 0 and 1, square root of x is upper function and lower function is x square. So once we decide upper and lower function, our work is easy. Now we take the difference of upper function and lower function, or function at the top minus function at the bottom, and integral with respect to x from 0 to 1. Now this is easy to integrate. We can use the formula of x raised to n. We are familiar with this formula. Integral of x raised to n is given by x raised to n plus 1 divided by n plus 1. N is different from minus 1. Here power of x is 1/2. Here it is 2. So this is going to be x raised to 1/2 plus 1, that is 3 by 2 divided by 3 by 2, that I can rewrite as 2 by 3 minus x raised to 3 divided by 3, integral of x square. Limits of x are from 0 to 1. Upper limit is x equal to 1. So we have 2 by 3, 1 raised to 3 by 2 is 1, 1 raised to 3 is 1. So this is for x equal to 1, minus lower limit is 0. Here x is in the product, so this is going to be 0. And 2 by 3 minus 1 by 3 is 1 by 3. So required area between given curves is 1 by 3. So in this way we can easily find out area between two curves. We just have to remember that we first find out the intersecting points of given curves. That is the first step we will consider. Find intersecting points of given curves. Second step is sketch the region enclosed by given curves, or sketch the region bounded by given curves. So whatever region you sketch, boundaries of that region must be given curves. Here upper boundary is of y equal to square root of x, lower boundary is for y equal to x square. So that is the meaning of region bounded by curves. Whatever region we will sketch, its boundaries must be given curves. And once we sketch the region bounded by given curves, we will be able to decide which function is upper function and which function is lower function, and we will be able to decide the limits of integration also. To find out limits of x, we will consider the leftmost point and rightmost points of the region, and the value of x at leftmost point is lower limit, value of x at rightmost point is upper limit. And once we decide limits of integration and this upper and lower function, we will use this formula. Area is given by integral from 0 to 1, integral of the difference of upper function and lower function. Okay, and then this is simple integration. So in this way we can find out area between two curves. Okay, sometimes they ask the problems related to area between two curves also. So this is easy. This is just the revision of 12th standard. Suppose I consider this function gx equal to 0. I will obtain this formula for area. Suppose lower function is 0. We will have this type of case. This is y equal to fx and we consider gx equal to 0, and we know that area of area of the region below y equal to fx from x equal to a to b is given by integral a to b fx dx. This we study in 12th standard, and we are generalizing this to the area between two curves. So this is simply the generalization of this formula. If we take lower function as 0, we will obtain this area formula. Okay, fine. So this is all about this session. I hope you like it. Thank you.